Hello, welcome to another module in this massive open online course. So, we are looking at example problems in duality. Let us continue our discussion. Alright, so what we want to look at is duality and some problems. To understand this, well, what we are seeing is, let us look at this problem. This is, for example, problem number 9. We want to find the dual of the problem, minimize the maximum of 1 less than or equal to I less than or equal to m ai bar transpose x bar plus bi. Okay. And this is known as a piecewise linear model. Okay. For instance, what you can see is each of these represents a line. Therefore, if you look at these different lines and now you take the maximum, so the maximum will have look something like this. So, these are m different lines and this is how the maximum looks like, and you can generalize this n dimensions for hyperplanes. All right. So, this is the maximum, which you can see is basically not exactly linear, this is piecewise linear. Okay. So, this is piecewise linear. So, in each segment you have a linear. So, in each segment you have a linear characteristic for this. Okay. And now what we want to do is we want to minimize. Now, I can write this. Now, to find the dual problem of this, what I am going to do is I am going to first you look at minimize the maximum of I equals 1 to up to m a bar transpose x bar plus bi. Now, first I am going to write this in the epigraph form. So, using the epigraph form, this can be equivalently written as minimize t subject to the constraint that the objective, which is basically maximum of a bar transpose x bar plus bi, I equal to 1 to up to m, this is less than or equal to t. Okay. So, this is basically our constraint. Now, obviously, since the maximum is less than or equal to t, this basically implies that each of these is less than or equal to t, which means a1 bar transpose x bar plus b1 is less than or equal to t, a2 bar transpose x bar plus b2 is less than or equal to t, so on am bar transpose x bar plus bm bar is less than or equal to t. Okay. So, I can write this basically as the equivalent optimization problem, minimize t subject to the constraint that ai bar transpose x bar plus bi less than or equal to t for I equals 1 to up to m. This is a much simpler form and this is something that is tractable. Now, I am going to develop the dual for this. Alright. So, this is the equivalent form and now we can focus on getting the dual of this problem. And the dual of this problem is obtained as follows. Now, first you form the Lagrangian L of x bar, in fact L of x bar comma t comma, since we have inequality constraints, that is lambda bar, okay, which is basically, now you take the objective t plus summation I equals 1 to m, one Lagrange multiplier for each constraint, that is lambda I into ai bar transpose x bar plus bi minus t. Now, what we want to do is we want to group all the terms corresponding to each. For instance, this can be written as t plus summation of I equals 1 to m lambda I ai bar transpose into x bar plus summation of I equals 1 to m lambda I bi minus summation I equals 1 to m lambda into 1 to m lambda I into t. And now, if you look at this, this is nothing but summation of lambda I, this is 1 bar transpose lambda bar, this is summation lambda I bi. So, you can write this as lambda bar transpose b bar. I mean, I think you know what the definitions of these are. These are basically vector of lambda 1, lambda bar is vector of lambda 1, lambda 2 up to lambda m, b bar is a vector of b1, b2 up to bm, and so on. And therefore, now if you simplify this, what I get is basically, I can write this in compact form as 1 minus 1 bar transpose lambda bar into t, that is sum 1 bar transpose lambda bar is nothing but summation of all lambda I, plus you can simply write this, take the transpose of this. So, I can write this as x bar transpose summation I equal to 1 to m ai bar into lambda I. So, it is very convenient to write it that way, x bar transpose, well, summation I equal to 1 to m ai bar into lambda, a bar into lambda I, and lambda I into a bar, does not matter, plus you have this quantity lambda bar transpose b bar, that is summation lambda I bi, which is basically lambda bar transpose b bar. Now, observe something very interesting. This is linear in t, linear in x bar, observe the, or affine, this is affine in t comma x bar, basically, which means it is a hyperplane, okay. And hyperplane, if the slope is not 0, it goes to minus infinity, which means if either 1 minus 1 bar transpose, I mean, of course, we have to take the minimum of this. So, now to get, I am sorry, there is one more step, that is the dual is basically getting the minimum of, with respect to x bar t comma lambda bar, which is basically, now you write this a little elaborately. This is minimum, by the way, for x bar comma t or the primal variables x bar comma t, 1 minus 1 bar transpose lambda bar into t plus summation or plus x bar transpose summation I equal to 1 to m lambda ai bar plus lambda bar transpose b bar. Now, you observe this is affine in t comma x bar, okay. Alright, which means it is a hyperplane. If the coefficients of t or x bar are not 0, it tend to minus infinity. Okay. So, if 1 minus 1 bar transpose lambda bar is not equal to 0, or summation I equal to 1 to m lambda I ai bar is not equal to 0, that means g of lambda bar equals infinity, minus infinity. Now, minus infinity is still a lower bound, but as we have seen previously, minus infinity is not an interesting lower bound. Okay. So, this is not something that we would like to work with. Okay. I mean, minus infinity is also a lower bound for the original optimization problem. So, but this is not very interesting for the simple reason that minus infinity is the lower bound for any optimization problem, any minimization. So, this is not interesting. So, what is interesting on the other hand, when the coefficients are 0, that is 1 equals 1 bar transpose lambda bar, summation of all lambda is 1, and summation I equals 1 to m lambda I ai bar equal to 0, which means if you write this as a matrix in matrix form, you have the vector a1 bar, a2 bar up to am bar times lambda 1, lambda 2 up to lambda, and this equal to 0. This implies that a times lambda bar equal to 0. Now, if 1 equals 1 times lambda bar and a times lambda bar equal to 0, then the minimum is the minimum of x bar comma lambda bar comma mu bar, and this minimum you can see is nothing but lambda bar transpose b bar. So, this minimum for that scenario is lambda bar transpose lambda, but the minimum is lambda bar transpose. Of course, now in the original when you formulate the Lagrangian, you have to also ensure that, remember, these are lambda bars are component wise greater than or equal to 0. So, this is true, minimum is lambda bar transpose b bar provided lambda bar is component wise. So, lambda bar is component wise greater than or equal to 0, and therefore, the dual problem can be formulated as now interestingly, that is maximize g lambda bar, that is maximize the dual function, which is maximize lambda bar transpose b bar, subject to the constraint that 1 bar transpose lambda bar equals 1, summation of all lambda I equals 1, a times lambda bar equals 0, lambda lies in the null space of A. Alright. So, remember, look at this, this is an interesting condition. This means that lambda lies in null space lambda lies in the null space of matrix A, and further non-negativity of the Lagrange multipliers associated with the inequality constraints, that is lambda bar greater than or equal to 0. This is the dual problem. Dual problem for the given the original minimax problem, that is minimization of the piecewise linear function. Alright, can be written in a linear program in this form. Alright. Let us look at another interesting application. We want to derive the dual minimize the negative summation of log of bi minus ei bar transpose x bar. This problem is arises frequently in practice. This is termed as analytic analytic centering, also termed as the analytic centering problem. Alright, so, we are going to minimize this summation I equal to 1 to m log bi minus a. Of course, the domain of this is pi greater than or equal to a bar transpose x bar. So, this implies a bar transpose x bar has to be less than or equal to bi for I equals 1 to m, that is the domain of x bar. Okay. So, you have basically this is an intersection of, as we know, half spaces. So, this is a polyhedron. So, the domain is basically this is basically a polyhedron. And to develop the dual, again what we will do is we will use a simple substitution. We will substitute yi equals bi minus ai bar transpose x bar. So, therefore, the optimization problem can be equivalently written as minimize minus summation I equal to 1 to m log yi, that is the natural logarithm of yi, subject to the constraint that each yi equals bi minus ai bar transpose x bar, subject to the constraint that y1 equals b1 minus a1 bar transpose x bar, y2 equals b2 minus a2 bar transpose x bar, and ym equal to bm minus am bar transpose x bar. And in fact, you can stack these things as a vector. Once you stack these things as a vector, what you get is the following thing. You can write this as y bar equals b bar minus matrix A or matrix A times x bar. What is A? A is the matrix A1 bar transpose, A2 bar transpose up to AM bar. Okay. So, I can write this. So, basically I can write this equivalently as minimize minus summation I equals 1 to m log yi subject to the constraint y bar equals b bar minus ax bar. Now, what I am going to do again to develop the dual, I am going to write this, I am going to form the Lagrangian, and from that minimize it over the primal the primal variables. Okay. So, the Lagrangian is lambda x bar comma y bar comma, now there are equality constraints. So, I am going to use nu bar, which is basically the objective, minus summation I equal to 1 to m log yi plus summation I equal to 1 to m, one Lagrange multiplier for each equality constraint, that is yi minus bi minus ai bar transpose x bar. Now, once again collecting all the terms, what you will observe is this will become summation I equals 1 to m, first collecting the terms corresponding to yi I equal to 1 to m minus log yi plus nu I times yi plus, once again collecting all the terms corresponding to x bar, this will be summation I equals 1 to m nu I ai bar transpose times x bar nu I into ai bar transpose into x bar and minus summation I equal to 1 to m nu I bi. This is going to be minus bi plus ai bar transpose x bar. So, this is going to be plus nu I ai bar transpose x bar minus 2. Okay. So, this is basically the Lagrangian. Okay. And now we have to take the infimum over the Lagrangian, alright, with respect to the primal variables, okay, but that is basically y bar and x bar. So, now what we are going to do is g of nu bar is the minimum over x bar comma y bar of x bar comma nu bar, which is equal to the minimum over x bar comma y bar. Well, we have the original, I am going to just simply write it minus summation I equal to 1 to m or I equal to 1 to m minus log yi plus nu I yi plus summation I equal to 1 to m ai bar transpose nu I into x bar minus, now of course summation of nu I bi, I can simply write this as nu bar transpose b bar just for brevity, which is minus nu bar transpose b bar. Okay. Now again you can see the following thing, this is affine in x bar, affine in x bar, implies if summation I equal to 1 to m ai bar transpose nu I not equal to 0, then your g of nu bar, that is the minimum, minus infinity, that is the minimum of this, because it is an affine function, minimum is 0, which is not interesting. Once again this is not interesting. Therefore, on the other hand, if summation I equal to 1 to m nu I a bar transpose nu I equal to 0, this implies, if you look at this, a m bar transpose into nu bar equal to 0, or basically a times nu bar equal to 0, then of course this is not an affine function. So, we would like to consider this condition. So, now we would like to consider this condition a times, because we still have this other part, which is, now let us come to this part, minus log yi plus nu I yi. Let us look at what is the minimum of this. Consider minus log yi plus nu I times yi. Let us call this phi of yi. Now, we have to find minimum of this, or minimum of basically phi of y. So, to do that, first differentiate this with respect to phi I yi, that is minus yi plus nu I equal to 0, which implies the minimum occurs for, well, yi equals 1 over nu I. And what is the minimum? Minimum value equals nu I into 1 over nu I minus log 1 over nu I, which is basically 1 plus log nu I. So, in summary, if A times nu bar equal to 0, the minimum occurs for, the minimum is basically the minimum of each log yi plus nu I yi is basically, so the minimum of each of this equals basically 1 plus log nu I, and therefore the net minimum is this 1 plus summation 1 plus log nu I minus nu bar transpose b bar. So, basically what you have is g of lambda bar equals minimum of L of x bar comma y bar comma mu bar. I am sorry, this is g of nu bar, and this is g of nu bar, which is basically, which is, you can see, summation I equals 1 to m log of nu I plus 1 minus, well, b bar transpose nu bar or nu bar transpose b bar, which is, if you take the constant 1, that is basically m plus summation I equals 1 to m log nu I minus b bar transpose nu bar, and of course subject to the constraint, remember a into nu bar equal to 0, otherwise it is minus infinity, which is not interesting. And therefore, the dual problem is, the dual problem of this analytical center is maximize the dual function, which is m plus summation I equal to 1 to m log of nu I minus b bar transpose nu bar, subject to the constraint that a times nu bar equal to 0, that nu lies in the null space of A. Okay, this is very interesting. Nu lies in the null space of, nu lies nu lies in the null space of A, and you can see basically what A is. A is A1 bar transpose, A2 bar transpose, AM bar transpose. So, A nu bar or nu bar lies in the null space, A nu bar equal to 0 implies basically each AI bar transpose nu bar equal to 0, which means basically nu bar is orthogonal in nu I bar is orthogonal, nu bar is orthogonal to each AI bar. So, nu bar lies in the null space of the matrix, alright. So, these are some examples of various problems, dual problems, convex optimization problems, and how to formulate their dual problems, which is often yield very useful insights, and these are often very useful in practice, especially for practical application. Alright, so let us stop here and continue in the subsequent modules. Thank you very much.